All right, recording is rolling. It is Thursday, January 12th. And actually, we're a few minutes into class already because I did the stand with the slinky. We stretched across the room. We pulsed across some longitudinal waves. We did some transverse waves, did some standing waves, count wavelengths. All right, so the kickstarted class. One of the things we're going to do today are these textbook puzzles from chapter 14 and 15. Chapter 14 is vibration waves, chapter 15 is sound. Okay. Before we get to that, wish you guys a really famous bridge collapse. And then lead into that too. So switch screen over. Yeah. Let's start with Chase from California here.
My name is Chase, and I live in
no
California,
humans.
and I'm gonna try to break this wine glass by only my voice.
Who's dying? Oh, I see people do this with their voice.
Yeah, so hit the resonant frequency of that glass, right? Now, a lot of materials and structures will have some associated resonant frequency. If you hit it and you keep driving in the energy, then well, that'll happen, right? It happened to buildings too, happened to bridges. We're about to look at that. So sort of what's the physics around this? You guys remember standing waves, like setting up standing waves? In fact, started this class standing wave set with the slinky one, right? All right, so what we got, Williams? We got speeds, frequencies, wavelengths. Ooh, do you guys think that this glass has like some circumference around it? And what if you set up a standing wave where the wavelength was like so multiple or matched the circumference of that glass? Ooh, and I bet there would be some frequency that would be associated with that, because speed equals wavelength times frequency. There's some speed of sound that's unique for each material. I bet there's a speed of sound in glass that I imagine is probably faster than in air. Sound usually travels faster through solids than through air, right? So speed of sound through glass is whatever it is, right? Wavelengths, like so multiple you care about of the circumference of that glass. There's some associated frequency, and if you hit that pitch, and you just happen to hit the pitch, right? That resonant frequency that would make this happen. Dana?
Can I have a new one of the lab papers? I don't know.
Oh, lab paper. Let me see what I got here. You're looking for this lab paper?
Yeah.
All right. All right. So, I remember even went to University of Florida, and one of the buildings they have there, O'Connell Center, it's like this dome type building. And since I was an engineering student there, one of the stories heard circulating was that when they were building that O dome, one of the things they were worried about was they realized that the resonant frequency of that structure was about 2 hertz. And 2 hertz, well, that'd be easy to chant to, right? Like, go Gators, go Gators, go Gators. If you have like a whole stance of people like all doing the same thing, there was a risk that could possibly fall apart. Let's look at a really famous bridge collapse that I think you may have seen this, maybe some of you guys, Tacoma Narrows. We're going back to 1940. 1940. So this bridge is going to open in 1940. And opening day, it kind of bounces up and down. Wasn't really supposed to, but engineers are keeping an eye on it, saying, all right, well, it's not really cracking apart, so we'll just keep using it, right? And then one day, this type motion happens. Oh boy, oh boy. There's a car parked out there. There's an engineer like walking around on the Snowdell line. He did get off the bridge before it collapsed though. So he's just checking out the bridge.
This is what anxiety would do.
No, right. Oh, guys, what is that bridge made out of?
It looks like it's made out of water.
Yeah, that's what it looks like, right? How about concrete? Yeah, concrete and steel. Yeah, that right there is a concrete and steel bridge. Right? There was a lot to be learned from this engineering wise. I'll show you guys after I flip the video back. Okay. Oh, do you guys see
Dude,
do you guys see a time period of about 5 seconds about to go back and forth to oscillate once? It's about 5 seconds. hey, what's the frequency of that motion then? The time period's 5 seconds. What's the frequency?
What's the? formula for frequency?
It's like 1 over the time period.
Oh, okay, so 1/5.
Yeah, 1/5 hertz. Okay, so 0.2 hertz, right? 0.2 hertz. 1/5 seconds is 0.2 hertz. There you go. So that's the resonant frequency of that bridge. Oh, and what do you think is supplying the energy? Like, what's keeping it going? Not spontaneously. There, wind. That's it, wind. Yeah. So really strong crosswind. There happened to be that day. So yeah, strong crosswind. Boom. There you go. And then let's get to
Relax, understand. Yo, get this.
there it is. Yeah. Basically, they caught that 1940. Yeah, true. But you guys see those columns? The support columns look perfectly fine, right? So they actually just went back and rebuilt this bridge, and with a little bit different design, of course.
One that didn't have 5 point, but one that didn't have obstruction, that, the one that isn't easily destroyed by, what was it, 1/5 hertz?
Yeah, pretty much, right? Yeah, so yeah, 0.2 hertz, but yeah, take that down. Okay. So when they originally built this bridge, the design and the original construction, they think, well, there's gonna be a bunch of cars going across the top. That's a lot of weight. How do you carry a lot of weight? Oh, well, you have vertically oriented structures. So in this case, they had these vertical girders, okay, all these vertical girders going on. Okay. And that was able to, well, at least on paper, that would be able to handle the weight of the cars. That seemed all fine and good, right? Okay. But in the real world, of course, there are lots of other forces that maybe they weren't thinking about in the design phase, right? Like that horizontal crosswind. And this would be terrible at handling any kind of horizontal type forces, right? So vertical is great, but horizontal or anything other than perfectly vertical, stop. So what do you think they did? How do you think they fixed this? Instead of vertical girders, what do you think they did?
Hexagon, triangle,
Triangles? You guys like triangles?
hexagon and triangle are great.
Guys like truss system? Truss?
That's very good.
Yeah, that's so exactly. Okay. Okay. In fact, if any of you guys go into engineering one day, there's a whole class called statics where they make a big deal about looking at truss structures and picking any particular point. At any particular point, the sum of the forces is equal to what? Zero, right? So you say, okay, sum forces is 0. That's x-axis, y-axis. That's true. You can figure out like what's the tension or compression on each one of these bits and exactly what that is. Do you guys think in a general case, this bridge might want to bend kind of this way, right? Do you think that would put the bottom here into tension?
Yeah.
And the top part kind of into compression, sort of? I bet this bit's probably in compression. This bit right here is like probably in tension. Okay. Okay. So truss structure. All right. Let's look at guys' puzzles. So this is posted to Google Classroom. We'll do what we normally do. I'll go over with the guys in class. Okay. Actually, I'm gonna throw a couple on here too. We'll just do today. This got kind of cut off here, but we're doing these. We're doing all 4 on the left side. We're doing 75, 77, 83. Actually, that's probably about as far as we'll get today. Okay. But later on, we're doing, oh, yeah, see this, yeah.
Oh, I also don't think I got that either.
Right. And in the future, we're doing 87, 88. No, that's chapter 14, vibration waves. Chapter 15 is sound, which is for type of wave. Do 52, 53, cut down here in the corner. 68, 71. 83, 93. Alright, so that's gonna be our adventure. What papers?
Yeah.
Alright.
I got it.
Alright, so everybody got this page? See this page? Okay. It's right here.
Oh, my gosh.
All right, so I got those. We're good. All right, so We're gonna do a few extra ones actually today, because like you guys see this one with the apples? Like originally I didn't assign that and a couple other ones, because those are way too easy, but yeah, we started doing these my earlier classes, and students really struggle with these, which kind of surprised me. I mean, for one reason, it's just kind of your lab yesterday. So yeah, let's do this. All right, we got these apples. Now, these apples weigh 3.2 newtons. Okay, so it's like a weight, like a force, 3.2 newtons of weight. Okay. And that causes the spring to stretch 0.12 meters. It's 0.12 meters. That's like 12 centimeters, right? So the question is, what's the spring constant? What's the spring constant? I want to see if anybody in here can get this before I show you guys. What is the spring constant of that spring? How stiff is that spring? All right, who figured it out?
I'm pretty sure it's on there.
Yeah. Yeah, you guys did this yesterday. It's like the first half of a two-part lab yesterday.
Yeah, it's on the lab.
Okay, so let's see, there's a force, there's some amount that stretches, and the spring constant relates to those two, right? Okay. Is that called Hooke's law? Hooke's law? You put a force, a spring stretches it. Okay. So you guys remember Hooke's law? F equals kx. You guys remember that? Right?
Oh,
You guys applied this yesterday? Right? See, they told you these two. They're asking for, what is that right there? So wouldn't the spring constant just be however much force do you put on it, it stretches so much? Okay. So
okay, so it's 3.2 over 0.12.
yeah, 3.2 newtons on 0.12 meters. That sounds right.
Yeah.
Yeah,
Yeah.
46.12 newton per meter. All right, all right. Right, guys got that? All right, so that's number 69. Just Hooke's law. And you guys saw that last semester too, right? Next one. How much potential energy is stored in a spring with a spring constant of 27 newton per meter, which, by the way, kind of matches what we just got. So, right? When it's stretched 16 centimeters. Ooh.
Oh,
dude,
that's like MDA. Right?
kind of it.
Oh, wait, no, kx squared, 1/2 kx squared.
1/2 kx squared. Ah, remember it. Yeah. Energy stored in the spring is 1/2 kx squared. You guys remember that? That's a good way to get it. Okay. Another question that would lead to the same answer is how much work was done stretching the spring? Same thing. Did you guys convert centimeters to meters first? You guys did do that? Centimeters, you converted to meters?
Okay.
So 71. Okay. They told you the spring constant was 27 newton per meter. And they told you the stretch amount was, well, we're going to use 0.16 meters, keep everything base SI units. Right? So how much energy stored in the spring? Okay. And Rose saying one way you can do this is just say, hey, energy stored in the spring is 1/2 kx squared. Remember that from last semester. 27 newton per meter. 6 meters being squared. Okay. Okay, so number on my screen says 0.3456. Now we'll round that a little bit to 0.35.
Yeah, that's what,
Because that's 0.35 what? What's the unit?
Newton meters?
See, Newton is a force.
It's not Newton meters? I thought.
Oh yeah, and Newton meter. Yeah, true. Newton meters, true. You can also call that
Joules?
joules. Yeah, there you go, joules.
Okay.
Yeah, Newton times meters is joules. Yeah. Well, of course, you're talking about torque, then you just say Newton meter, but yeah. So energy in joules. There you go. Let me show you guys an alternate way you could have also solved that. So that's like the algebraic way, but it's also like a graphical way to do it. Okay. Force in newtons, stretch amount in meters. No, if it doesn't stretch at all, then there's no force to get there. So that's the point of the graph. Okay. Because if you graph that, you make a graph for stretching a spring. The more force you put, the more it stretches. Right? What does that graph look like?
Linear up.
Yeah, linear. Because again, that's just Hooke's law, F equals Kx. So we got K is here, which in this case it's like 27 Newton per meter. Okay, the slope of that line. Okay. And we're going all the way to bam, 0.16 meters right there. Now, guys, what property of this graph tells you the energy stored in the spring?
The integral.
Yeah, the integral. Yeah, integral is a good one, right? Which is the area of that triangle, right? You guys remember work is equal to force times distance, right? But in this case, it's a variable force, so the force is always changing. Times so I split this up into a bunch of little bits, right? Say a little force, then more force, more force, more force, more force, add up all the bits. Okay. Hey, I wonder how much force we're putting on to stretch it to that point. How much force is that? Well, F equals Kx, right? 27 Newton per meter, 0.16 meters. That 4.32 newtons of force. Right? So the area of a triangle is 1/2 base height. It's 1/2 base height. Right? So 1/2 base height. Hey, it's the same thing. Same thing. Okay. There you go. Two different ways to do it. Number 73. Oh, look at that. Force versus stretch distance. That's what we just did, sort of. Right? Just different numbers. But same thing. What is the spring constant of the spring?
Well,
Yeah, the slope. All right. Slope. And so who's got a number for that?
20.
20 Newton per meter. All right. 20 Newton per meter. All right. You guys are doing better in my earlier classes. That is cool. So got F equals Kx. Therefore, K is F over X. That's like rise over run of the graph. You guys pick that out pretty fast. So okay, so 1 point could be the origin 0.00. If you put it on 12 newtons, it stretches 0.6 meters. Therefore, 20 Newton per meter is the slope of the graph and the spring constant. So spring. That's part A. Part B. What is the energy stored in the spring when it stretches to 0.5 meters? How much energy? Another way to say that is how much work did it take stretching it that much? 0.5 meters. Yeah, how much? Yeah, that's one way to do it. Area under the curve. Yeah, up to, of course, the 0.5 meter mark. Yeah, let's do that. Oh, yeah. What'd you get?
It's 2.5 joules, I think.
2.5 joules. That's it. 2.5 joules. Right. So you can either do 1/2 kx squared, which would be 1/2 times k times x squared is 2.5 joules. All right. Or area. Yeah, let's do area. So you get 0.2, sorry, whoops, 0.50 meters. And that's 10 newtons at that point. Bam, right there. So area of that triangle, let's just make sure. So let's 1/2 times base times height. Yep, that's also 2.5 joules of energy stored in that spring. Yeah, two different ways to do it. Okay, 74. How long should a pendulum be to have a time period of 2.3 seconds on the moon, where gravity field is only 1.6 meters per second squared? So we're looking for a time period of 2.3 seconds, and gravity field is 1.6 meters per second squared on the moon. So how long is the pendulum? Let me pause this recording. Pause. Recording is resumed. All right. So what did you guys get for the time period for that pendulum? Or sorry, not the time period. The length.
I just did the equation and switched around the variables. Now I'm actually plugging it into the calculator.
All right.
2 pi LG.
Boom. That one right there. That's what everybody's looking at, right? Just like that. It's your lab a couple days back. Okay. Right, so they just told you these two, check, and they're asking, solve for that. Is it? Yeah, what'd you get?
3.30625,
Huh.
is that right?
Yeah, it's a little different. Okay. So, yeah, so you're right. You're starting with that. Okay. You answered it to your lab a couple days back. Okay. They gave you bam, and you're solving for that guy right there. Now you can plug in the numbers first, that's fine. I'll start in terms of variables. It's a good skill to have, right? Start in terms of variables. Now what you're solving for is buried underneath the square root. At some point you need to square both sides, so just went ahead and took care of that first. Okay. Ooh, I bet you can take this 2 pi quantity squared, divide it down, and cross multiply with the g, and that would isolate length, right? Okay, so there's the general expression for length in terms of everything else. Okay. Then you just feed in the numbers they gave you. Okay. And I got that right there. 0.21 meters. Now 0.21 meters, is that called 21 centimeters? Okay. Oh, 21 centimeter pendulum. We can make a 21 centimeter pendulum. It's about this right here.
Oh, I typed the wrong thing in the calculator.
All right, okay, yeah, that's what happened then. Do you guys see 21 centimeter pendulum on Earth? See how that's really close to a 1 second time period? Tick,
Yeah, okay,
Tick,
I got the same thing.
tick, tick. That's really close to 1 second. Okay. But of course on the moon, where gravity is really weak, it slows it way down. In fact, it slows it all the way down to 2.3 seconds on the moon. All right.
Yeah, okay, that was the same thing you did.
All right. Yeah. Got it. 75, building motion. Sears Tower in Chicago sways back and forth with a frequency of 0.12 hertz. What is the time period of vibration?
Oh, fine.
Well, 0.12 hertz. Hertz is 1/seconds. Cycles per second. Okay. You can tell me how much time does it take to swing back and forth?
What did you say, Red Blood?
Hertz is 1/seconds.
Oh, 1/, oh, okay, so it's like 100/12 would be 8.33.
Bam, 8.3 seconds. Nice. Great. You guys remember frequency is 1 over the time period. Therefore, time period is 1 over the frequency. They're just reciprocals of each other, right? So time period is 1 over 0.12 hertz. Now hertz is 1/seconds. Seconds comes back up on top, describes the time period. Yeah, well, yeah, you got the answer, right?
You
8
say
point-
the power -1.
Yeah, power -1 will do it too. Yeah, you're right. Like that, right? Yeah. All right. A little over 8 seconds. Swing back and forth. 77. Waterways in a shallow dish are 6 centimeters long. At one point, the water moves up and down 4.8 oscillations per second. Is that called a frequency of 4.8 hertz? Couple questions. What's the speed of the wave and what's the time period of the waves? So 77. Okay. Suppose there was like a flat bed of water, maybe a pond or something, right? And you go and tap it like tap. Right? You watch the ripples move out. You see all those ripples moving out. Okay. Then we'll get down near the surface and we're watching them from the side. From the side, it looks like. Doop, 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 doop. So we're watching these ripples like propagate out. And they told us the wavelength is 6 centimeters. So maybe take a snapshot, break out a ruler, say, hey, how long is it from crest to crest? And that wavelength is 6 centimeters. So you got 6 centimeter wavelength. Okay. That's the smallest bit that'll repeat. Okay. And the other thing they told you is that suppose you're watching a leaf bob up and down. So we put a leaf on the water right here. So this leaf is just like floating on the water, right? And it's bobbing up and down. It bobs up and down 4.8 oscillations every second, which is pretty fast, right? So it's like
That would not happen.
yeah, but we're just throwing it. Yeah, all right. Okay, so let's pick a leaf, right? Maybe some planet with a lot of gravity or something. Right? It's pretty close. Right, so we got a frequency of 4.8 hertz. Okay. Guys, what formula do we need to solve this? It's like the most important wave formula. speed equals,
lambda f.
yeah, wavelength and frequency, right? Wavelength meters, frequency 1/seconds, meters per second, meters per second. Go bam. If you ever forget how to put a formula together, think about how the units work, right? Because help you piece it back together. So we got 6 centimeters, 4.8. I'll say 1/seconds per hertz, right? 1/seconds.
28.8.
Yeah. 28.8 meters per second is the wave speed. That's how fast that wave is propagating through the water.
The time to be 0.2083.
That sounds right too. Yeah. Right. And how'd you get that?
I took it to the power of -1. I said the hertz.
Oh, yeah. Right. 4.8 to the power of -1. That'll do it. Okay. This is just
Flip it.
reciprocal, right?
You just flip it over. Yeah, it's reciprocal.
Yeah. So let's try it that way. Yeah. 0.21 seconds. Okay. That's the time between flips, right? Blip, 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 blip.
I thought it was. Okay.
Right. All right. Go. Right. And then another physics connection with materials in the real world. There usually like is some speed that some wave will propagate through some particular material, right? And then like if you know one of these things, you can figure out the other things sort of. Right. Right. Let's. Oh, okay. Wow, I think we're making really good time because you guys are doing real good here. Right, earthquakes. The velocity of transverse waves is 8.9 kilometers per second, and longitudinal waves is 5.1 kilometers per second. Right, so different waves traveling at different speeds. A seismograph records arrival of transverse waves 68 seconds before the longitudinal. How far away is the earthquake? Actually, yeah, looking at that, I just realized wording this like halfway through today is I've always been teaching it the other way around, that longitudinal travels faster than transverse, but anyway, I got some demo sign for you guys, so I'll have to look into that and see if I got my facts straight on that. But let's look at some earthquake type demos and talk a little bit about seismology here. Okay. So there are whenever an earthquake hits, there's actually 2 different kinds of waves sent out to the world, and they travel at different speeds, so they'll hit you at different times. Do you guys see that the bottom ones are longitudinal and the top ones are transverse? Okay. And in earthquake terminology, they're called P waves and S waves.
Do you remember the repeat thing I showed you about?
The what?
Where you press the 3 dots? And you
Oh, yeah, true. That is a good tip. Let's do that. Yeah, thanks. What's it? Yeah. All right. Yeah, good call. Good call. I'll start using that one. Yeah, thanks. So, now I've heard P and S could stand for pressure and shear, which is true because that is a pressure wave and that is a shear wave, right? That type motion. I've also heard primary and secondary, which I think is also accurate, but although that, again, you just realized like halfway through today, that's opposite of what your book said, right? At least how I've always been teaching is that like primary travels faster than secondary, so it hits you first and it's primary. So anyway, we'll solve the numbers from the book though, right? Now, let's actually see these play out. So here's well, we're about to see footage from the earthquake that hit Fukushima a little over 10 years ago. Looking at a pool of water, right? Here's about when the P waves are hitting. Notice the water is still calm, right? So when the P waves hit, you have like, that gives you a warning, gives you a few seconds of warning to either get under something sturdy or get outside or, get out of the way of everything, get out of the water. Okay. Ooh, looks like that might be about the S right there. Okay. It's all crazy.
P waves are the longitudinal ones, right?
Yeah, P waves are longitudinal, S waves are, bam, the shear waves.
What's in a pool?
Huh?
You see that thing in the pool?
Ooh.
Just going around with the wave.
This ball here. Oh yeah,
Ball? Okay.
or maybe, I don't know. Something. Yeah, so very crazy looking, right? Right, so you guys ever see say like earthquake and then shown on the news and say, hey, we know exactly where the epicenter is, and they pull out a map and say like happened, bam, right there on the map. How do they know that? Okay. Well, here's how they know. So all over the earth are these different seismograph stations. Okay, you got this roll of paper, right, rolling all day, every day, just rolling. Okay. And got this ink pen, has a huge mass, huge inertia, connected to a spring, connected to the world. Right? And then usually this is real boring because all day, every day, just leaves like a straight flat line. It's like, okay, well, that's not much. Right. Until an earthquake hits. Earthquake hits, let's break open this paper and go back and look at it. Right? Doesn't the entire world start shaking? Right? But if you have a huge inertia right here, and connected to the world by a spring, a lot of that earthquake energy is really hard to get through that spring. And we have a huge mass here. So the pin stays still and the entire world moves around. Okay? So this is going to look like here's the P waves, and then bam, and then there's the S waves. Okay. It goes. Now, what if the seismograph station was right on top of the epicenter? Right? Would there be any warning at all? No, it's like bam, happy birthday. You just get the S waves. Now, but the further away you are, the fact that these waves travel at different speeds, right, you get more and more of a warning, right? And if you know what these different speeds are, then you can figure out if you know the time and the speed, you can calculate the distance, right? And then if you start calling up a bunch of other seismograph stations, let's say there's this guy here and this guy here and this guy here, and they're like hundreds of kilometers apart. They say, hey, how far away is the earthquake from you? Yeah, right. Okay. So this guy says 100 kilometers away. So they draw a 100-kilometer radius. This guy said, hey, it was 150 kilometers away from me. 150 kilometers, so a little further away. Okay. And then call this guy, said it was 100-something kilometers away from me. Okay. So then you got like 3 circles. See, like if you only had 2, it'd be ambiguous. You wouldn't know. But you bring in the third guy, say, bam, it's right here. You determine the epicenter. Okay. Right, then you call up a 4th station. Maybe this guy's like, oh, it's real close. It was just like right nearby. It was somewhere like what's this vicinity, right? So we're about to do the calculation to determine like how far away. And of course, you need like multiple stations. You need at least 3 stations to determine exactly where the epicenter is. So let's do the calculations for her. How far? Now this one's kind of fun. They told you the speed of. I'm actually going to swap this, I think. I'll call it speed of the primary as 8.9 kilometers per second, and the speed of the secondary is 5.1 kilometers per second. Right? This is number 83. 83. Okay. This will be the last one we do today. Right? Last one today, because as far as I've been getting all day. Right? Can you guys set up a one more thing. The time interval. So I'll say delta t. The time between the two is 68 seconds. So the primary hits, and then 68 seconds later, bam, the secondary hits. Okay. Now, can you guys set up a system of equations that you could eventually solve to figure out how far away the epicenter is? Right. How far away? That sounds like x, doesn't it? X. We got speeds and times. Hey, guys, is distance equals to speed times time? Ooh, so the distance, I bet it's 8.9 kilometers per second times the primary time. And I bet that same distance is 5.1 kilometers per second times the secondary time. Would that be true?
So you set them equal to each other?
Yeah, you can set them equal to each other is no, that could be one step you could do. No, thing is though, there'd still be 2 unknowns. Like right now, there's 3 unknowns.
Oh,
Right.
yeah. Okay.
So we still need one more equation. And that's this guy right here. Right, the time gap. So time secondary minus time primary is 68 seconds. Okay. This right here is your complete system of equations. Right. Now there's multiple ways to solve systems of equations, but yeah, let's do what you said, which is set these top 2 equal to each other. Then we can, okay, so we'll work it from there. We'll do one step at a time. So the fact that it's the same distance, I can say 8.9 kilometers per second times time primary must be equal to 5.1 kilometers per second times time secondary. We'll multiply right here, right? So that's the relationship between TP and TS, but here's a different relationship between TP and TS. Okay, hey, can I add TP over and say that I'm taking this guy and just rearrange him by himself. The secondary time is primary time plus 68 seconds. That would also make sense, right? Okay. And then I could take this expression and substitute it right in there. Okay. You guys do see we're kind of in the middle of just the long algebra process, right? Okay. So really, the critical thinking part is like, can you set up the system? And now we're just into the algebra like the rest. Okay, so let's put that right in there. 8.9 TP is equal to 5.1 times TP plus 68. I'll drop the units just for a couple of steps, just to make it look a little cleaner. Can I distribute that 5.1 kilometers per second? Okay, so 8.9 TP is equal to 5.1 TP plus, let's see what this is. It's 5.1 by 68, 346.8. Okay. Kilometers per second, kilometers in this case, kilometers per second, Okay. Subtract this over, divide by the coefficient. 8.9 minus 5.1. 3.8 kilometers per second times time primary is 346.8 kilometers. Then divide down this coefficient. 346.8 divided by 3.8. Time primary is 91.3 seconds. Rounding a little bit. Do that right. Okay, you guys good? Ooh, yeah, we're making good time today. So, I'll do a little bit of extra math just to show that everything works no matter how you solve it. Okay. I mean, if this is true for time primary time, hey, I wonder what the secondary time was. It's just that plus 68, isn't it? Here, time secondary is just this number plus 68 seconds. Plus 68. That's 159.3 seconds. Okay, some of that too. So I got time primary, time secondary. Okay, let's go back to the original setup. So I've got two different ways now I can get x. They should both agree with each other, right? Okay. So let's do how far away is the epicenter? It's 8.9 kilometers per second times 91.3 seconds. 8.9 times 91.3, which is 812.6 kilometers. Or the other way to do it is 5.1 kilometers per second times 159.3 seconds. See what that is. 5.1 times 159.3, which is 812.4 kilometers. Okay, so rounding a little bit along the way, you guys see those are basically matched, right? Okay, there you go. That's how far away the epicenter is. All right, and then we're just back to all this stuff. Call this guy. So 812 kilometers away. Sweep out a circle around this guy. Okay, and then you just need to call some other stations to figure out where exactly the epicenter was. I'm gonna Google this whole E wave S wave thing. All right. Yeah, okay, because I just Googled this and it says according to Google, P waves do travel faster than S waves. Okay, so I have been teaching it right all along the years. That's good news for me, but bad news for your textbook. So your textbook has the numbers backwards, but that's okay. That's what that would be. All right, let's call that a wrap on today.